Assalamualaikum and hi everyone. Today I want to teach about the second law of thermodynamics. Before that, we have learned about the thermodynamics, the first law of thermodynamics. I want to recap a little bit about it. In chapter 5 and 5, we had applied it, our first law of thermodynamics, which is the principle of conversation, which is happened in open ecosystem. Alright, now the second law of thermodynamics, which is mean that the process occurred in a certain direction, not in any direction. For example, I take for the pedal wheel. Consider a pedal wheel mechanism that is operated by the flow of mass. The pedal wheel rotates as the mass falls and still affect within an insulated container, right? As a result, the potential energy of the mass decreases, and the internal energy of the fluid increases according to the conservation of energy principle. However, the reverse process, raising the mass by transferring heat from the fluid to the pedal wheel, does not occur in nature, although doing so would not violate the first law of thermodynamics. So here the diagram of the pedal wheel. Okay, next we proceed to the thermal energy reservoirs. In the development of the second law of thermodynamics, it's very convenient to have a hypothetical body with a relatively large thermal energy capacity, which is mass times with capacity. Then that can supply or absorb finite amounts of heat without change in temperature. Okay, here's we got two phase of system, which is condenser and boiler. From the condenser, heat will be out, which is energy sink, such as like atmosphere, lake, ocean, and etc. Here is the reservoirs that absorb heat at the sink, and then it proceeds to the energy source. Energy source like furnace the heat will into the boiler. So the heat source, the reservoir that supplies the heat. Okay, now proceed to the heat engine. Actually, work can be converted to heat directly and completely, but converting heat to work requires the useful of some special devices, which is heat engine. Okay, heat engine is any device that converts heat energy into useful works. Alright, here I will explain how this turbine, this heat engine work. Okay. Firstly is from top edge, which is heat temperature heat reservoirs. Here is the heat source like furnace. Okay, and over here is heat sink, atmosphere, or ocean, or river, and etc. Okay. First is they receive heat from a high temperature like solar energy or furnace, and then they convert part of this heat to work, usually in the form of rotating shaft, and then they reject the remaining waste heat to a low temperature sink at the atmosphere, river, or ocean at the bottom place, and then the amount of work will in this at the pump, and the work will out at the turbine. So they operate on a cycle. Then the work net is equal to work out minus work in, and the Q net is equal to Q in minus Q out. For the closed system, which is for cycle, closed system is Q minus W heat minus work is equal to delta U, which is internal energy. We consider it is a zero, okay, because it is in closed system. So the heat equal to work in closed system only. Closed system only. Right, now we proceed to the thermal efficiency. Actually, the thermal efficiency is from this equation, which is work net output is equal to Q in minus 2 Q out. So this is net work output must be divided to total heat input. So here is the symbol of thermal efficiency, like this, okay? And the thermal efficiency must be is equal to 1 minus Q out over Q in, and also 1 minus QL over QH. And the Q out is not equal to 0, okay? And the work net output must be less than heat in. So the thermal efficiency is a measure of how efficiently a heat engine converts the heat that we receive to work. Okay, now we proceed to the cabin plus statement and cost process statement. And then, this statement is provided from which is produced because of the heat out cannot be saved, which is actually the heat out cannot be saved because the condenser cannot accept all the heat. So cabin plus statement, it is impossible for any device that operates on a cycle to receive heat from a single reservoir and produce a net amount of work. So this is the schematic diagram, which is same from the previous in the thermal energy reservoir. So here is heat higher and heat lower. Heat lower must be equal to 0. Okay, and this and the turbine work net output will move out. And then the process, right? The Kelvin statement is happen in the heat engine. And then here is no heat engine can have a thermal efficiency of 100%. Or as for a power plant to operate, the working fluid must exchange heat with the environment. And next, the process. Process happen in refrigerator and heat pumps. So it is impossible to transfer energy from a cooler to water body without leaving on effect of to the surrounding. So here is the schematic diagram, which is from warm environment at temperature higher must be greater than temperature lower. And then, so here is cold refrigerated space at temperature lower. Here is compressor. Here is valve, expansion valve. Right, here is evaporator. And up here is condenser. Okay. the word from here we move in, the word that we here we move in into the compressor. At here we assume that the pressure here, pressure at compressor and pressure at expansion is same. Pressure at compressor and the compressor will help the expansion valve to move up the temperature. Here we consider it 60 degrees Celsius, here we consider it 30 degrees Celsius. Will help move up to the condenser. So here is required input. Where the word let in, and at the here is QH, here is QL, and here is desired output. Alright, now I want to talk about COP, which is coefficient of performance. Actually, it is the efficiency of refrigerator and heat pump expressed in COP. Here is COP refrigerator, which is the objective of it to remove the heat of heat lower from the refrigerator space, while the COP of heat pumps is to maintain the refrigerated space at a low temperature by removing heat from it. So here is the calculation for refrigerator first. Okay? Desired output must be divided by the required input equal to QL over work net in equal to QL over Q I minus QL. We can simplify in this 1 over QH over QR minus 1. So for the COP heat pump equal to same goes to this, same goes to the refrigerator, which is desired output divide required input, and QH is divided by work net in, and we can simplify QH over QH minus QL, and then lastly we got this 1 over 1 minus QL over QH. So the difference between COP refrigerator and COP heat pump is, which is here, we have QL and QH. Here we use heat lower, and this heat pump. At heat pump we use heat higher. Okay, now we proceed to the reversible and irreversible process. First of all, I want to talk to reversible process. Alright. It's defined as a process that can be reversed without leaving any trace on the surrounding. Alright. Example on. I give an example for frictionless pendulum. This pendulum will move and will oscillate from left to the right without leaving any trace. And then next, the second example is quasi-equilibrium, which is inside this have gas and having a compression. Quasi-equilibrium. Expansion. Gas expansion. Alright. Okay, next is irreversible process, which is mean a process that are not reversible. That are not reversible. Okay? This process consists three is occur due to first is friction. Occur due to friction. Okay? It causes heat transfer. Without heat pump. Next is cannot use this lost energy to reverse the process. So second is heat transfer, which is finite delta T. It cannot reverse the process without heat pump. That is electricity required for heat pump would affect the environment. So it is bad, maybe have a bad consequence to our Earth. Quasi-static process and non-quasi-static process. First, I show you for quasi-static process, which is slower. It is irreversible. So here the diagram, which is in this one. Uniform pressure is move out, and is also uniform pressure. Here is work out is equal to PdV is related at 0. And here is work in it's equal to degree PdV must be less than 0, or work net is equal to 0. So for non-persistent process, which is known as fast process, and also irreversible. Here is the diagram. What is about higher pressure is above and lower pressure is below at the bottom. Work out is equal to PdV, and must be greater than 0. This work is moving. Here is high pressure at here and low pressure at here. And work in is equal to, so here P lower, and here is P higher, dV. And none must be less than 0, or then work net is less than 0. Right. Now we discuss about Carnot cycle. First, we have to define about what is the Carnot cycle. Carnot is a process that operates under a reversible cycle. This is the PV diagram, which is where the this expansion, what happened inside of this. You can know it through this PV diagram. Okay. There are 4 reversible, which is here 1 to 2. Process 1 to 2 is known as reversible isothermal expansion. Here is isothermal expansion, and next is process between 2 and 3 is known as reversible elevated expansion. And process 3 to 4 is known as also isothermal compression, because it is different way. Process 4 to 1 is elevated compression. So at this process, between process 1 to reversible isothermal expansion, the heat addition at high temperature, which is here is T higher is greater than T lower, where TH is constant. TH is constant. Okay. So at the process from 2 to 3 is elevated process, elevated expansion, which is working free temperature decrease from TH to working temperature decrease from TH to TL. So from process 3 to 4 is the system is brought in contact with heat reservoir and T lower must be less than T higher. So at the process 4 to 1, the decompression, which is increase the working fluid temperature from TL to TH. All this expansion and compression is all this in reversible. So next is a Carnot refrigeration cycle. This cycle is inverse from the Carnot cycle, which is the direction. And here is same 1, 2, 3, and 4. The difference is the directions only. And oh, if I forgot, here is got Q height enter and Q lower is out. While here is Q high is out and Q in, Q L is in. So here is also the temperature higher is also constant. And at the number also change, which is here 1, 4, 3, 2. At 3, at the 3 stage, TL also constant. Okay. The reverse Carnot cycle process, it becomes Carnot refrigeration cycle. Cycle remains exactly the same except the direction of heat and work interaction are reversed. Heat lower is absorbed from a low temperature reservoir, while heat higher is ejected from high temperature reservoir. So and the work net in is required to accomplish all the process. Alright, now we proceed to the Carnot principles. Right, the efficiency of irreversible heat engine. The heat engines is always less than the efficiency of a reversible one operating between the same of two reservoirs. So the efficiency of all reversible heat engines operating between the same two constant temperature heat reservoirs have the same efficiency. So here is the high temperature reservoir at high temperature, and but 1, 2, and 3. First is irreversible heat engines. Second is reversible heat engine. Third, reversible heat engine. So the efficiency between 1 and 2, 1 is less than 2, while the efficiency between 2 and 3 is equal. And the lower is the bottom one is the lower temperature reservoir at temperature lower. Okay. Now is the Carnot heat engine. Okay. It is a Carnot engine that operates on the reversible Carnot cycle. So the thermal efficiency of the engine is this. The efficiency is 1 minus QL over QH. For the reversible, efficiency is 1 minus TL over TH, where TL and TH are absolute temperature, which is in Kelvin. So I want you to remember about 3D sign. When the efficiency efficiency less than the efficiency reversible, it is irreversible heat engine. When it is equal, it is reversible heat engine. When it less than efficiency reversible, it is possible heat engine. So I want to bear in mind with this sign. So next is the Carnot refrigerator and heat pump. So this equation we just learned about it just now. So we just recall it back. For COP refrigerator, 1 minus QL over QH minus 1. For COP heat pump, 1 over 1 minus QL over C over QH. Also can be expressed as for COPR refrigerator, 1 over TL over TH minus 1. And for COP heat pump reversible is 1 over 1 minus TL over TH. And also where TL and TH are absolute temperature in Kelvin. So please make sure you are not confused with this equation for refrigerator and heat pump. Which one is divided and which one is 1 divided by 1. Okay? So we proceed to also we proceed to COP sign. Okay? COPR or HP. Greater, equal, and less than, equal, and greater than. And this one for COPR or HP reversible. If less than, it is reversible. HP or R. If equal is reversible. HP or R. And also if greater than is impossible. Same with previous one. Okay? And for the coefficient is of performance of actual and reversible Carnot refrigerator or heat pump operating between the same temperature can be compared as follows. Okay? So thermodynamic temperature scale can be applied for relation to the heat transfer between a reversible device and the height with the height and low temperature by this expression. QH over QL reversible is equal to TH over TL. So the QH over QL ratio can be replaced by TH over TL. For the reversible device, where TH and TL we use in absolute where is absolute temperature. Now we do the some exercise. I picked the exercise from sheet 4.2, which is Right. A household refrigerator with a COP of 1.2 remove heat from the refrigerated space at a rate of 60 kilojoule per minute. So, determine the electrical consumed by the refrigerator. So, we can calculate it like this, right? Work net in is equal to QL over COP of refrigerator. So we just insert this one and this one. 60 kilojoule per minute over 1.2. So we got the work is 50 kilojoule per minute. So the answer is the electrical power. So the answer is 0.83 kilowatt. We just change it to the power. Okay. So for question B is determine the rate of heat transfer to the kitchen area. So the QH is equal to QL plus W net in. So the QL is 60 and the WN is 50. So the answer is 1.4 kilojoule per minute. Next question is exercise 6.4. A refrigerant 1348 enters the condenser of a residential heat pump at 800 kilopascal and 35 degrees Celsius at a rate 0.01 kilogram per second and leave at 800 kPa as a saturated liquid. So if the compressor consumes 1.2 kilowatt of power, determine the COP of the heat pump. So this question wants the COP. The compressor. So this question wants us to determine the COP of the heat pump. Here in this question we have been given the power, which is 1.2 kilowatt. So we assume the heat pump operates steadily and the kinetic and the potential energy change to zero. Okay. So P1 is 800 kilopascal, T1 is 35 degrees Celsius, P2 is also 800 kilopascal, and S2 is 0. So we have to find the H. This H we can find it at the table at the back of the book, which is 27.22 kilojoule per kg, and H2 is 95.47 kilojoule per kg. So we can insert in our equation, which is H1 and H2. Mass has been given, rate of mass, so just put it is H1 27.22 minus H2 95.47. So we get the answer 3.64 kilowatt. Okay. So the next question is the rate of heat absorption from the outside air. Oh, before that, we want the COP. So the COP is equal to QH over work. So 3.614 is equal over to 1.2 kilowatt. We get the answer is 2.64 for the COP. So the question B is Q low is equal to QH minus WNE. So we just get the QH is 3.164, while the WN is 1.2. So the answer we got it is 1.69 kilowatt. Okay. So I hope you guys understand what we learned today, and thank you for watching.